Welcome to Mrs. Z's Chemistry. In this video, we will talk about stoichiometry with leftovers and limiting reactants. So let's take a look at this example. We have this chemical reaction where 1 mole of SO3 reacts with 1 mole of H2O and it produces 1 mole of H2SO4. The problem says if you have 3 moles of SO3 and 2.5 moles of H2O, how many moles of H2SO4 can be produced? Previously, we've only ever been given one amount of one of the reactants, and we are assuming or being told that the other reactant has enough. We have enough of the other reactant in order to completely react the one that we're given. Here, though, we are given two different amounts, one for each of the reactants. So we need to figure out which one runs out first, because then once one of the reactants runs out, we can't make any more product. Because these two reactants, SO3 and H2O, react in a 1-to-1 ratio, we can see that the H2O, which has the fewer amount of moles, 2.5 versus only 3, will run out first. Now remember that it's okay to react, even though this reacts in a 1-to-1 molecule ratio, it also reacts in a 1-to-1 mole ratio, which means you can react a decimal number of, or a fraction of, a mole. Because a mole is this huge number, a small fraction of this number is still a whole number of particles or molecules. So we know that the water runs out first. So we're going to use the 2.5 moles of water because this one is the one that's going to dictate how many products we can make. We don't do any math with the 3 moles of SO3. We have enough SO3 to completely react the water, and then once the water runs out, the reaction stops. Yes, we'll have some leftover of SO3, but the problem isn't asking about SO3. It's asking how much product can be made. So we use our mole ratio between water and the product. The coefficients come from the chemical reaction. We have a 1-to-1 mole ratio, and we get to produce 2.5 moles of H2SO4. Oops. The second part says which reactant is limiting the amount of product that can be made. Well, that is H2O. When it's talking about which reactant, that is a compound, that's not a number. So water is one of the two reactants, and water is the one that is limiting the amount of product that can be made. So here's the definition. The limiting reactant is the reactant that runs out first. It limits the amount of product that can be made. The excess reactant is the other one. It's the one that doesn't run out first. And there's still some left over after that limiting reactant runs out. So here's another example. We have 2 moles of Na reacting with 1 mole of diatomic fluorine, and that turns into 2 NaF. This is just the balanced chemical reaction. The problem tells us if you have 5 moles of each reactant, how many moles of the product NaF are produced? So we have 5 moles of each, 5 moles of Na. Each particle here, or circle, is representing 1 mole of the substance. And then we have also 5 moles of diatomic fluorine. In chemical reactions, chemical reactants are going to break their bonds and then reform. And so we get to break a bond here between the diatomic fluorine, and we're going to create our products. We're going to keep creating products until we run out. The product is NaF. And we are creating them here. So now we have run out of sodium. The Na runs out first. It is the limiting reactant, and we have made 5 moles of NaF. That is the answer to this problem. How many moles of NaF are produced? Only 5 moles. Yes, we have some fluorine left over. We have 2.5 moles of fluorine. No, we don't have just half a molecule of diatomic fluorine, but we do have half a mole of diatomic fluorine left over. So here's the math of how this would work. Once you figure out that sodium is the limiting reactant, we use sodium in the problem. The 5 moles of sodium is what we get to completely react, so that's the one we start with. We only get to start with the amount that gets completely reacted. The mole ratio is 2 moles of sodium to 2 moles of NaF. and that is how we get to produce 5 moles of NaF. So this is the math and the unit conversions behind what just happened with all of the particles up here. All right, so the next problem says, if you have 2.5 grams of each reactant, how many moles of NaF are produced? Before, in the previous problem, we were told we have 5 moles of each. Now we have an equal amount of mass. But this 2-to-1 ratio between our reactants is not a mass ratio, it's a mole ratio. So we have to convert these 2.5 grams of each into moles of each of those reactants. Pause to see if you can work this part out before moving ahead in the video. All right, so I've got the first step done here. We have our 2.5 grams of sodium. Using the molar mass of sodium, we get 0.109 moles of sodium. That is how many moles is in the 2.5 grams of sodium. We also have 2.5 grams of diatomic fluorine. Diatomic fluorine has this molar mass, 38 grams per mole. So therefore, we have 0.0658 moles of fluorine. Now that we're in moles, we can compare our 2-to-1 mole ratio and see if we can figure out which one is going to run out first. 0.0658 moles of fluorine is the smaller amount of mole, so maybe that's the one that runs out first. Let's do a double check here. If we were to completely react all of our 0.0658 moles of fluorine, we would need twice that of sodium in order to completely react it. Twice that of sodium, because of the 1-to-2 ratio, is 0.1316. So in order to react all of the fluorine, we would need 0.01316 moles of sodium, but we don't have that much. So that means we can't react all of the fluorine. The sodium is going to run out first before all the fluorine gets reacted, and fluorine is going to be the one in excess with a leftover amount. Therefore, the 0.109 moles of sodium is what gets completely reacted. That's the limiting reactant. And let's do a double check here. Because of the 2-to-1 ratio, we only need half of this amount of sodium, of fluorine. So we have half of 0.109 is 0.0545 moles of fluorine. That is how many moles of fluorine we need to completely react the 0.109 moles of sodium. And we have enough. We have more moles of fluorine than that. So this is what we do. We start with the 0.109 moles of sodium, and we use this in our mole ratio to see how much product was made, because it's asking how many moles of NaF are produced. The mole ratio is moles of sodium on bottom and moles of NaF on top. The mole ratio here is a 2 to 2. So that means we produced 0.109 moles of NaF. Yes, we have some fluorine left over, but the problem is not asking about that. All right, here we have a new chemical reaction. It is a 2-to-1-to-2 mole ratio. After 1 gram of each reactant are placed in the same beaker, part 1 says how many grams of KCl are formed, and part 2 says how many grams of the excess reactant are formed. In order to find the mole, to use the mole ratio of 2 to 1 here to figure out which one runs out first, we're going to convert to moles. So we have 1 gram of each reactant. 1 gram of potassium. The molar mass of potassium is this. Pause to see if you can solve this before you move on to see the video, the rest of the video. One gram of chlorine. The molar mass of chlorine is 70.9. Don't forget it is diatomic, so that is 2 chlorines added up together. So this is 0.141 moles of chlorine. So we have to first figure out which one runs out first, and then figure out how many grams of KCl are formed. But then we also want to find out how many grams of the excess reactant are left. So both of these problems are a little bit tricky to work out. I have a chart to help us figure this out. Let's look at this. It is called the BCA table, before, change, after, and it's going to help us determine the limiting reactant and how much is left over of the excess reactant, as well as how much product is made. Here's the important part. All values must be in moles in this chart, because it is going to follow the mole ratio that's given in the chemical reaction. So we just found how many moles we have of each. The 1 gram of each gives us 0.256, oops, that is actually 0.0256 moles of potassium. So we write this in here. And then we also have 0.0141 moles of chlorine. This is how much we have before the chemicals are mixed together. Before the chemicals are mixed together, we have 0 of the product. Now, the change row must be in ratio of 2 to 1 to 2. So we need to figure out which number runs out first. If chlorine were to run out first and we subtract all 0.0141 moles of chlorine, then we would need twice that of potassium. Twice that of potassium, though, is 0.0282, and we don't have that much. You can't use up more potassium than what we have. So this tells us that potassium is actually the limiting reactant. So we're going to use up all of the potassium, 0.0256, and we only need half of that of the chlorine, 0.0128, and we have enough chlorine in order to react all of the potassium. The potassium chloride that is produced is going to be in same ratio as the potassium because this is a 2 to 2 ratio, so it should be the same number. Really quick, let's take a look at this change row again. So we're going to look at this change row. We have 0.0256, 0.0128, and 0.0256. That is in ratio of 2 to 1 to 2, which is exactly what we have in the coefficients. The reactants, the potassium and the chlorine, they are subtracting. We have a negative amount because we're using them up. All of the products should have positive or a plus sign, not just positive, but a plus sign in the change row, whether you have one product or two products. Now, the after column or after row is going to be the before minus the change, 0. Before minus the change, this is 0.0141 minus 0.0128. And then we have 0 plus 0.0256 is 0.0256. Now we can see that we have this table all filled out, and we can see at a glance that potassium is the limiting reactant, chlorine is the excess reactant, and this is how many moles we have left over, and this is how many moles of the product is produced. So let's go back to the problem. The first problem here says that asks for how many grams of potassium chloride are formed. Well, we know that we formed 0.0256 moles of it. So then we would just use the molar mass of potassium chloride. Potassium has a molar mass of 39.1 and chlorine is 35.453. That gives us a molar mass of 74.533 grams of KCl. The unit on all of these should be KCl. And then if we multiply that by the 0.0256, the answer to this is 1.91, if we're going to round to 3 sig figs, grams of KCl was produced. Then the second problem says how many grams of the excess reactant is left over. Chlorine is the excess reactant because we have some left over, and the amount of moles we have left over is 0.0013 moles of chlorine. The molar mass of chlorine, remember that it is diatomic, is 70.9 grams of chlorine. So 0.0013 times the 70.9 gives us 0.092 grams of diatomic chlorine.